Nowadays, computer vision systems are capable of detecting objects, recognizing people, and they can also extract numbers and text directly from digital images and videos. Think about license plates. How do cameras scanning traffic instantly read them? They're all powered by sophisticated mathematical algorithms. License plate recognition is based on a task known as digit recognition. It's basically a classification problem. To each portion of an image containing a number, we want to assign the corresponding category, that is, a number from 0 to 9. But how can an algorithm perform this task? First, we need to recall how a computer sees images. As we have already seen, to a computer, an image is a structure grid made of tiny squares called pixels. In grayscale images, each pixel holds a value ranging from 0 for black to 255 for white. And these values are collected in a matrix organized in rows and columns depending on the pixel position in the image. A digit recognition algorithm processes the input matrix to associate the image to the correct category. And one of the most popular approaches uses these so-called convolutional neural networks, a class of deep learning model designed to process images. A typical convolutional neural network involves 4 processing steps, each handled by a different layer of the model. First, a convolutional layer finds visual patterns. It scans the input matrix with filters to highlight important features of the images, such as a straight line, curves, or edges. Then, a pooling layer compresses the information coming from the filter and collects the essential characteristics of the image. The flattening layer then arranges this data in a long linear vector. And finally, a dense neural network completes the classification task by mapping the compressed vector to a category, giving us the predicted digit. However, it's not so easy. As we will see later on, to work in this way, the network will need to be trained. But first, let's examine each one of these layers in detail. And actually, we start from the last one, the dense layer, to introduce some key concepts about neural networks such as nodes and weights. A standard dense neural network is made of interconnected nodes. Each node or neuron takes as input some numbers picked from a longer array. In this example, we have 3 values, x0, x1, and x2, that are combined to produce an output y. To do this, the neuron multiplies each input by a coefficient called weight, here w0, w1, and w2, and then adds another coefficient called bias, here indicated as b. The result is then passed to the function sigma, known as activation function, which modulates the incoming information. The weights and biases are adjustable, and their choice is crucial because it determines the neuron's sensitivity to input. The dense neural network can so be seen as a parameterized function that depends on all the weights and biases of its neuron. And we will investigate later on how to properly find them. The raw output of the dense layer is then processed by the softmax function. So what is it? The softmax function is used for multi-class classification. It converts the raw output score from the dense layer into a probability distribution over the possible classes, and the classes with the highest probability will be our answer. So now let's go back and let's see how the input for the dense layer is constructed. And actually, we need to start from the very beginning, from the first layer called convolutional layer. Given an image as input, its goal is to extract its most important features. And to do it, it uses convolution with filters. From week 4, we know that filters are small matrices, for instance, 3 by 3, with specific entries depending on the type of filters. When we apply a filter, we produce a new output matrix with a specific effect, and this effect sheds light on a specific feature, so these results are called feature images. But the features we're looking for are not known a priori, so also the entries of the filters are not given in advance. They must be found during training, just as the weights and the biases of the dense layer. And this way, the filters automatically adapt to the specific type of images that the model needs to process. Pooling is the second building block. It reduces the dimensionality of the input by processing groups of pixels. And there are different options for the pooling operation, but in our example, we present max pooling. Max pooling compresses the information by selecting the largest value among a group of pixels in the feature images produced by the convolutional layer. For instance, in this case, we process 16 groups of pixels, each of size 7 by 7, to extract their max. This layer produces smaller matrices, in this case 4 by 4, one for each filter. And finally, we need to map these small matrices resulting from max pooling into a vector that a dense neural network can take as input, and this transformation is made by flattening. In this example, flattening simply takes all the entries from the small 4 by 4 matrices coming from max pooling and lies them in a vector, which is the dense layer input. Now that we have examined each layer of the convolutional neural network, the next step is to select the optimal learnable coefficients. And as we have seen, the convolutional layer and the dense layer depend on a certain number of them, such as the entry of each filters, the weights, and the biases. To find the optimal values, we perform the so-called training procedure. We show the network many examples of already labeled images, process them, and evaluate the difference between the network answer and the truth. And based on this difference, we adjust the network coefficient. So let's have a look at the details. First, we need a collection of images and their actual values stored in a data set. The training process is then made of 5 steps. Step 1 is initialization. We simply assign random values to the parameters of the neural network. Step 2 is called forward propagation. Here, input data, the image, is passed through the network, generating a prediction. Step 3 is the calculation of a loss, a function that measures the difference between the prediction of the network, in this case 6, and the actual value, in this case 8. Step 4 is called backpropagation. And here we compute the gradient of the loss with respect to all the parameters of the network, moving backward through the network. And finally, step 5 consists in updating the weights and biases according to the gradient in the direction that minimizes the loss, so to reduce the discrepancy between the network prediction and the actual values of the digits. Now, step 2 to 5 are repeated many times with different input samples, gradually improving the network prediction performance. So summarizing, training is nothing else than the minimization of the loss with respect to the values of the network parameters. And in the following videos, we are going to see this in action by implementing in Python and MATLAB a digit classifier based on image processing and convolutional neural networks.